Okay, good morning and welcome to this next lecture on vibrations of plates and shells. We are in the topic of Rayleigh Ritz method. In the last lecture, we entered two-dimensional structures. So, one of the interesting or key papers you can say is this by Professor R.B. Bhatt, and we looked at his method of generating orthogonal polynomials and use it to find or estimate natural frequencies of rectangular plates. And so we gave a list of polynomial forms for, say, simply supported plates, clamped plates, and clamped free plates. Okay, I just want to list out some of the numbers. If you can access the paper, then of course you will know. So some numbers I will give you so that those who attempt can know. If you have a plate that is simply supported on all four sides, then we are going to list the root lambda parameter, okay, and the side ratio alpha, then we have mode number and some value that we compare with exact, then this method orthogonal polynomials. So the side ratio is 1, let us say, then the first mode, which is the 1,1 mode, the exact value is 19.739. then what you compute, you can obtain this value. Okay, he does not list the number of polynomials, or maybe he does. Okay, number of. Then second is the 1,2 mode, then 49.348. this also is 49.348. It's 2,1. This is a square plate, so you will get the same value. Okay. Now if we do it for another side ratio, which is say 2.5, the first mode is 1,1 is 71.555. this is also 71.555. then second mode 2,1 is 101.163 and 101.164, and third mode is 3,1 150.511 150.991. then let us say we consider a clamped plate on all sides, then the root lambda parameter for alpha 1, first mode 1,1 is 35.988, 35.9855. second mode is 2,1, third mode 1,2, this is 73.413, 73.395, the same value. Fourth 2,2, this is 108.27, 108.22. if you choose a ratio 1.5, you guessed first mode 1 is 60.772, This is 60.762. Then second mode is 2 comma 1, 93.86, 93.835. Third mode 1 comma 2, 148.82, 148.78. and fourth mode 3 comma 1, 149.74, 149.85, and lastly we have simply supported, free and free. Okay, so simply supported and simply supported, and then free and free. So for alpha you have 1, mode number is 1, quote unquote exact value 3.3687, and the orthogonal polynomial, that is the method of Professor Bhatt, 3.3671, 3.3671. The second is 17.407, 17.316. Third is 19.367, 19.293. Fourth is 38.291, 38.213. And for alpha of 2.5, first is 8.251, 8.247. Second is 29.646, and this is 29.567. Third is 64.76, here it is 65.078. Fourth 99.206, 98.737. Okay, for those who wish to calculate. Now there is another paper. Let me write the title here so that I use the space. Vibrations of circular plate with multiple eccentric perforations by Rayleigh Ritz method. Authors are K. Saeedi, Saidi, then A. Leo, then R.B. Bhatt, and I. Stiharu. And this is in Journal of mechanical science and technology. (26/5/2012), pages 1439 to 1448. Okay. Now what is or do the authors propose? They have a circular plate. They have a circular plate with some boundary condition, say clamped boundary condition, and inside they have holes, multiple holes. Okay, so we will not worry about the multiple holes, but we will worry about one central hole which makes it an annular plate, annular clamped plate, let's say clamped circular plate. The method is exactly the same. Okay, the kinetic energy function is formulated as rho h by 2 integral over the area w square r dr d theta. Okay, whatever be the area. If it is an annular plate, this is the area. Okay, and because it is polar coordinates, you need this r dr d theta. Then the potential energy is formulated as d over 2, again integral over the area del 2 w by del r square plus 1 over r del w by del r plus 1 over r square del 2 w by del theta square whole square minus twice 1 minus nu del 2 w del r square into 1 over r del w del r plus 1 over r square del 2 w del theta square plus twice 1 minus nu Poisson's ratio del r 1 over r del w del theta whole squared, close the bracket, r dr d theta. Okay, so nu is the Poisson's ratio and d is given by E h cube by 12 into 1 minus nu square. Okay, and what sort of functions, how do you choose the functions now? It's an annular plate, so this is inner radius, this is outer radius. So let me write that way. You choose first r comma theta, we choose in this form, which is phi 1, we will tell you phi 1 later, phi 1 r into a 1 0 cos 0 theta plus b 1 0 sin 0 theta, which is 0, okay, plus phi 1 of r A11 cos 1 theta plus B11 sin 1 theta plus phi 1 of r A12 cos 2 theta plus B12 sin 2 theta plus the higher level function in radial direction phi 2 of r, next function, then A20 cos 0 theta plus B20 sin 0 theta plus phi 2, same phi 2 r A21 cos 1 theta plus B21 sin 1 theta plus phi 2 of r A22 cos 2 theta plus B22 sin 2 theta and so forth. Okay. In a summation form, how does it look like? In a W of r and theta looks like summation m going from 1 to capital M, phi of m of r into n going from 0 to some n, a m n cos n theta plus b m n sin n theta. Okay. So, we are interested in a circular plate with a hole at the center. So, this is Ri and this is R. Okay. That is the configuration. We will look at, say, clamped for now, clamped on the outer boundary. Okay. So, now the first choice phi 1 of r is d1 r square minus capital R square whole square. Okay. Now, as was shown in the rectangular case, we can normalize phi 1 r right now or later. So, here we normalize right now. So, d1 constant is chosen such that integral 1 to r inner to r now, okay, phi 1 square of r dr, this r is now important, is equal to 1. Okay. Then what do? We take the phi 1 r, this phi 1 r, and then divide by the square root of phi 1 integral phi 1 square of r dr to the power half. Okay. You choose d1 such that this goes to 0, this goes to 1, okay, and then you divide this phi 1 r by this value. Okay. So, essentially what happens is, if I do, this is the new phi 1 r, this is the new phi 1 r. So, if I now integrate r I to r phi 1 square of r dr, then I will get 1. Okay. Now, so phi 1 is found. How do I find phi 2? Phi 2 of r is found r phi 1, okay, r times phi 1, and I have to take out phi 1 r from this. If I had vectors, two vectors a and b, a and b, then the component of b in a is a dot b. Okay, this is with respect to vectors. With respect to functions is the inner product. Inner product is the integral. Okay, integral f into g, that is the inner product of functions. So I have to take out the component of phi 1 out of r phi 1. So how do I do that? I take a minus, I integrate this r phi 1 and multiply by phi 1 and r dr. Okay, this much of phi 1 r has to be taken out. Okay, and this phi 1 r is already normalized, so we don't need any more normalization here. Okay, so now shall we check if phi 2 and phi 1 are orthogonal? So if I do inner to outer, phi 2 r into phi 1 of r dr, then I get integral r I to r, this term r phi 1 into phi 1 into r dr minus, this is already integrated, which is integral r I to r square phi 1 square dr, and now I have phi 1 r multiplied by phi 1 of r, just as I did here, bring and integrate from r I to r. Okay, but this is phi 1 square r dr, which is 1. Okay, so this is 1, and this is what r square phi 1 square, this is r square phi 1 square subtracted, so this is 0, which means phi 2 and phi 1 are orthogonal to each other. Then what do? You compute the new phi 2. New you compute. How do you compute? You do this you have phi 2 of r and you divide by the integral of r I to r phi 2 square of r into r dr, then take the square root and rename it as phi 2 r. Okay, necessarily I have too many in the list. Okay, now how do I do phi 3 as the last one I will show? Phi 3 is r times phi 2, but I need to take out the part of phi 1 in it and part of phi 2 in it. So first minus integral r I to r r phi 2 and dotted means just multiply phi 1 r dr and phi 1. Phi 1 minus integral r I to r phi 2 and dotted with phi 2 r dr into phi 2 into phi 2. Okay, they are all r functions. Now how do I know this is orthogonal to phi 2 and orthogonal to phi 1? Okay, so I do first with phi 2, let us say integral Ri to r phi 3 dotted with phi 2 into r dr. Okay, this is just a product, okay, not a dot product like vectors, is equal to r times phi 2 integrate Ri r, then multiply by phi 2 r dr, and I have this term, so I have to multiply here phi 2, right. So I have minus integral Ri to r square phi 2 phi 1 dr integral Ri to r phi 1 phi 2 r dr minus integral Ri to r square phi 2 square dr and integral Ri to r, this term phi 2 square r dr. Okay. Now we have already proved that phi 2 and phi 1 are orthogonal. So this integral is 0, so this term goes to 0. This term goes to 0. Now phi 2 square, here we normalized, so phi 2 square r dr is 1, so this is 1. Then I have r square phi 2 square r square phi 2 square with a minus, so this is 0, and therefore phi 3 and phi 2 are orthogonal. Okay. So similarly we can check Ri to r phi 3 with phi 1, so phi 3 phi 1 r dr is equal to integral Ri to r phi 2 phi 1 r dr, this term, minus integral Ri to r square phi 2 phi 1 dr, then integral Ri to r phi 1 square r dr, this term, minus integral Ri to r square phi 2 square dr, and this here integral Ri to r phi 2 phi 1 r dr. Now phi 2 phi 1 are orthogonal, we did that last time, so this term goes to 0. Phi 1 square r dr was orthonormalized, so this is 1. I have r square phi 2 phi 1 dr, r square phi 2 phi 1 dr with a minus, so this is also 0. So phi 3 and phi 1 are also orthogonal. Then you orthonormalize phi 3 again. Phi 3 is equal to phi 3 old by integral Ri to r phi 3 square r dr square root. Okay, like this you continue. So now you have a set. Okay, then you have generated your w r comma theta right in the beginning. Okay, then you start doing del Vm by del A10 minus omega square del psi m by del A10 etc. equal to 0. You generate all the set of equations and you get this generalized eigenvalue problem. Okay. Then you compute your omega squares, and the author plots what is lambda fourth is omega square is equal to rho h r to the power 4 omega square by d, and omega is listed. Okay, after taking some adequate number of terms, 10 terms or so. Okay, we are out of time, so I'll continue with this in the next class. Thank you.